Hello class, welcome to this video on AP Statistics, Chapter 7, Lesson 1, Sampling Distributions. So this whole unit is going to be on sampling distributions, and in 7.1 we're going to just kind of look at an introduction to what is a sampling distribution and, some properties, characteristics, things like that, and how do they differ from other distributions. Okay, so we're starting with learning target number 1. All right, so the first learning target is to distinguish between a parameter and a statistic. So a statistic is a number that describes some characteristic of a sample. Okay, remember the main thing of statistics is you are trying to study populations by taking a sample, right? And the sample should be representative of the population, right? So that you can learn something about the population. But sometimes it's too difficult to study the entire population, and that's why we take samples. And the information we get from the sample is a statistic, right? It's a number. So the parameter is a number that describes some characteristic of a population. And what we want to do is, ideally, the purpose is we want to estimate the parameter using the statistic, right? And in order to do that, we have to understand a little bit something of sampling distributions and how they work. There's some symbols here for the sample statistic. Okay, so we have the sample mean, that's the average, which is x bar. We've seen that before. And this is supposed to estimate the mean, right? Mu, the population mean. If we want to estimate the population proportion, p, sometimes we use pi for that as well, capital Pi, but it's not very common that we use that. Okay, so I'm going to put that in parentheses. Not commonly used. We usually use p, but you could use pi as well, capital Pi. But if we want to estimate the population proportion p, then we'll use p hat, okay, to estimate it. So this is the sample proportion. This is p hat. And if we want to estimate sigma, lowercase sigma, the standard deviation for the population, then we want to estimate that with the sample standard deviation, S, right, or SX. Okay, so it's important to understand that these population parameters here are usually in Greek, like if you include pi, mu, pi, sigma, or in this case you can use the little p. Whereas these are not, okay? So that's important to understand. All right, so example 1, we want to identify the population, the parameter, sample, and statistic. So the Gallup poll asked if 515 randomly selected U.S. adults if they believe in ghosts. Of the respondents, 160 said yes. Okay, so we want to determine what is the population. So in this case, the population we're taking 550 randomly selected U.S. adults out of the entire population of U.S. adults, right? So the idea that they're U.S. adults here gives us a clue that that's our population, right? So our population, we're pulling these people from all U.S. adults. Okay, and then we have 515 of them. So that's going to be our sample. We'll get to that. But the parameter is the population characteristic that we're studying. We're studying the proportion, right? The proportion of all U.S. adults who believe in ghosts. Okay. And remember the symbol, since it's proportion, right? We're dealing with the proportion. So it says, oh, the respondents, 160 said yes. Yeah. So we're dealing with the proportion. Proportion means percent. So here you're saying, oh, 160 out of 515, that's like a decimal or fraction or percent. So the proportion of all U.S. adults who believe in ghosts. And the symbol for proportion for the parameter is either P or capital Pi. And then we got the sample. The sample is the 515 randomly selected folks who were interviewed. Statistic. Now, what we're going to do is that the statistic is 160 out of 515 that say yes. So that's going to be my p hat. Okay, so p hat is the proportion and the sample who say they believe in ghosts, right? Which in this case was 160 out of 150, or out of I was going to say 151 out of 515, which is 0.31. Okay. All right. So part B, it says during the winter months, the temperatures outside the Starnes cabin in Colorado can stay well below freezing for weeks at a time. Um, to prevent the pipes from freezing, Mrs. Starnes sets the thermostat at 50 degrees Fahrenheit. She wants to know how low the temperature actually gets in the cabin. A digital thermometer records the indoor temperature at 20 randomly chosen times. Okay, so 20 randomly chosen times during a given day. Okay. The minimum reading is 38 degrees Fahrenheit. And okay, so in this case, it said the population is, well, the sample is 20 randomly chosen times during the day, right? So we know that. So that means the population is all the times during the day, right? So all times during the day in question. And parameter, which will, the parameter is in this case the minimum temperature, right? Because we're looking at the minimum reading. Okay, she wants to know how low the temperature gets. Okay, so this is a minimum temperature, the true minimum temperature reading in the cabin at all times in the day. Okay, so that's the parameter, and the sample is the 20 randomly chosen selected times. The statistic is going to be the sample minimum, right? Now there's not really a symbol for the sample minimum. So we just usually call it just sample minimum. Okay, so the sample minimum temperature. So there's no like universal symbol for that per se. And then we got 38 degrees Fahrenheit. Okay, all right. So hopefully that makes sense. Pause the video and try the check. All right. Hopefully you paused the video and attempted it. The question. So it says identify population parameter, the same things that we did in the previous. So from a large group of people who signed a card saying they intended to quit smoking, 1,000 people were selected at random. It turned out that 210 or 21% of these individuals had not smoked over the past 6 months. Okay, so it says from a large group of people who signed a card they intended. So we got a large group of people saying they intended to quit smoking. Okay, from these people you have 1,000 that were selected at random. And it says 210 or 21% of these individuals had not smoked over the past, um, looks like had not smoked over the past 6 months. All right, so that's what we're looking for. So the parameter or the population is all the people who did sign the card saying they were going to quit, right? They intended. So all people um, signing the card saying they intended to quit smoking. Okay, now out of all these people, 1,000 were randomly selected, and the parameter is we're trying to determine the percent of people who actually did quit smoking. So the proportion of the population who had not smoked over the past 6 months. Okay, who had not smoked. So we're going to use P for the population, the parameter, who had not smoked over the past 6 months. Okay. All right, so then we got the statistic, which is going to be p hat. Okay, so in this case, it's going to be the proportion in the sample who had not smoked over the past 6 years or 6 months. Over the past 6 months. Okay, and then they said that proportion was 0.21. All right, so notice that when we're dealing with these counts, out, this many out of whatever, we usually use a percent, a fraction, or a decimal, and we call that a proportion, all right? If we're dealing with the average, obviously you're going to be using mu and x bar. If you're dealing with a standard deviation, obviously you're going to use lowercase sigma and then the sx, okay, or s. So that's how you know the symbol, all right? That's it for learning target number 1. So number 2, it says create a sampling distribution using all possible samples from a small population. Okay, so we want to talk about this idea of sampling variability versus, sampling distribution. Okay, so sampling variability we've seen before. Every time you take a sample, different samples produce different results. Okay, and this is referred to as sampling variability. Okay, where the sample, the specific value of the sample, the sample that you take is going to be different, right? Every time you take it. So it refers to the fact that different random samples of the same size from the same population produce different results or different values for a statistic. Okay, so that's referred to as sampling variability, and it's just a fact of life that you're going to have something different every time you take a sample. And so because you have different results when you take a sample, you can graph these results, and these results would form part of what we call a sampling distribution. Okay, so the sampling distribution of a statistic. So again, these are important vocab terms to know. The sampling distribution statistic is the distribution of values taken by the statistic, because the statistic is a value from a sample, right? And all possible samples of the same size from the same population. Okay, so we'll show you an example of that. So it says, let's say we want to approximate the sampling distribution for a penny activity, okay? So for this penny activity, we are looking at the years of the penny, okay? So we have a pile of pennies. We choose, 5 random pennies, and then we average the years on the pennies, okay? So like 2005, 2010, whatever. We add those years up and divide by 5, okay? So we want to do an average. So basically, since we're doing an average, we're talking about a sample mean here. So that means we're talking about X bar, okay? So each of these values is an X bar. So for example, this X bar is 2010, so that indicates that if I took the 5 pennies and I averaged their years, by adding the years up, dividing by 5, I got to 2010, okay? And that's a data point. Okay, so each of these data points represents 5 pennies randomly chosen with their average year. Okay, now we did this 50 times, so there's 50 X bars here. All right, now this collection forms an approximate sampling distribution. So the more we do this, the more it's going to represent the true standard sampling distribution. Okay, all right, and we can see what the shape is and things like that, important information. We'll get to that in a second. So Mrs. Gallus took only 50 random samples of 5 pennies. However, there are many, many possible random samples of size 5 from Mrs. Gallus's large population of pennies. If the students took every one of those possible samples and calculated the value of X bar for each and graphed all those X bar values, then we would have a sampling distribution, okay? And this sampling distribution will be referred to as a sampling distribution of sample means. Sampling distribution of sample means. Because we're doing it for X bars. If it was P hats, then we would say the sampling distribution of sample proportions, or whatever, whatever you're doing. So this is a sampling distribution of sample means. So for large populations, it is too difficult to take all the possible samples to obtain the exact sampling distribution. But we can approximate it. Okay, so we can approximate it by taking many samples. So many samples, and then calculating the value of the statistic for each of the samples and graphing the result. Okay, so because the students in Mrs. Gallus's class didn't take all the possible values of 5 pennies, their dot plot of X bars, we said, is called an approximate, okay? Sampling distribution. Okay? All right, so there's there's the idea of the sampling distribution, the concept. So example 2, John and Carol have 4 grown sons. Their heights in inches are 71, 75, 72, and 68 inches. List all 6 possible samples of size 2. Calculate the mean of each sample and display the sampling distribution of the sample mean using a dot plot. Calculate the range of each sample and display the sampling distribution of sample range using a dot plot. Okay, so we have 2 parts here. So first let's do the mean and then we'll do the range, okay? Now we are trying to come up with all the possibilities of size 2. So our n is 2, okay? So this is n equal to 2. Where we have 2 per sample, or 2 in each sample. All right, so what are all the possibilities of these 4 data points where I select 2 at a time? How many possibilities are there anyways? Well, it turns out we can calculate that using what we did in chapter 6, okay? Lesson 3, the recent lesson. To calculate that, we do a combination, all right? So it turns out that I have 4 objects taken 2 at a time, right? 4 objects, and I want 2 of them at a time. And we showed you how to calculate this. Is 4 factorial over 2 factorial times 4 minus 2 factorial. And remember, factorial means you multiply, right? So 4 factorial is 4 times 3 times 2 times 1. And then 2 factorial is 2 times 1. And then this is another 2 factorial, so it's another 2 times 1. So 4 times 3 times 2 is 24, and then 2 times 2 is 4. So there are 6 ways that we can do this. So in our list, we should have 6 possibilities. Okay, so that's one way to do it. You can just calculate like that. And then you can do all this in the calculator. You don't have to show this calculation, all right? Because this can do it. The calculator can do this for you. All right, so we have 71 and 75. We can do 71 and 72. Right? So those are some possibilities. We can also do 71 and 68, right? 71, 68. We can do 75 and 72. Then we can do 75, 68, and 72, 68. Those are all 6 possibilities. All right, and we might as well list them here as well. This is the same data, the same thing. Okay, so now that we have all the possibilities of sample size 2, we're going to do the sample mean of each. Okay, so remember the sample mean is when you add them up, divided by 2. So how did we get this? We got this by doing 71 plus 75 divided by 2. Right, and we got this by doing 71 plus 72 divided by 2. All right, and then so we're going to do the same thing here, right? We're going to do 71 plus 68 divided by 2. So let's see, 71 and 69.5. Okay, so that's good. And then again, do the same thing, 75 plus 72 divided by 2, so that's 73.5. All right, so now we're gonna graph these in here, and this is gonna form our sampling distribution of sample means. Okay, all right, so we got 73, so dot there. We got 71.5, which is right here, 69.5, 73.5. 71.5, so another 71.5, and then 70. And this forms our sampling distribution of sample means, okay? So let me write this out. Sampling distribution of X bar, or sample means, right? Okay, So now we're going to do the same thing for the range. This time our statistic is going to be range, okay, sample range. So the range is when you subtract the largest minus the smallest, okay? So the way we got this is 75 minus 71, right? The way we got this is 72 minus 71. All right, so we got 71 minus 68, that's 3. That's how we got that. And then 75 minus 72, again, that's 3. Okay, so those are my sample ranges. We're gonna of course graph them. So this one's not too bad. So 1, 2 3s, 2 4s, and a 7. So this is referred to as the sampling distribution of sample range. Sample ranges. All right, for this particular example. All right, so now we are going to, and oh, that should be it. So we've done the dot plot, we've done the possibilities. Okay, good. All right, so go ahead and pause the video and see if you can attempt the following problem. I'll scroll down so you can see the data here. Okay, there you go. All right, hopefully you paused the video and you attempted the problem. Here's an example dot plot where we're going to graph them. Okay. Okay, so using the data to answer the question. So we got Abigail, Bobby, Carlos, Deanna, Emily, and then we got their genders and then the quiz score. So now part A, list all 10 possible simple random samples of size n equals 3. Calculate the minimum quiz score for each sample. All right. Okay, and this should say not sample proportion female. This should say minimum or sample minimum. So let me change this. I should say sample minimum. Sample minimum. Okay. All right, so let's go ahead and do that. Okay, so first of all, how many possibilities do we have for n equals 3? If we're choosing, if we have, let's see, we have how many people do we have here? 1, 2, 3, 4, 5. We have 5 people. All right, so for n equals 3, it says we have 10 possibilities, but let's do that. So 5, choose 3. That's 5 factorial over 3 factorial times 5 minus 3 factorial, which is 2 factorial. And 5 factorial, 5 times 4 times 3 factorial. Now, this is a trick that I'm using because we know that 5 factorial is 5 times 4 times 3 times 2 times 1. But I'm not going to finish it because I'm going to cancel that 3 factorial with the 3 factorial right here. So that's a cool little trick that you can do. And 2 factorial is just 2 times 1, which is just 2. So we have 20 divided by 2 is 10. There you go. And then for n equals 2, we've already I think we've already calculated that, so I'm not going to do that here. So there's 10 possibilities, all right? Which I already said that there, but just so you know how to calculate that. All right, so let's list out the 10 possibilities of 3 people. So we have A for, I'm just going to say A for Abby, Abigail, B for Bobby, and C for Carlos, okay? So we have A, B, C. We have, we can do A, B, D for Deanna. We can do A, B, E. We can do A, yeah, I'm just gonna use their first initial here. We could do A, C, D, right? So these are all the possible, these are just listing out all of them. We could do A, C, D. We could do A, D, E. Then we can go to the B's. So let's try B, C, D, B, C, E, and B, D, E. I didn't do that one yet. And I think that's it for the B. Let's see. 3, 4, 5, 6, 7, 8. That's 8 so far. Okay. I noticed I forgot ACE, so let me do that here. I like to put it in order. You don't have to put it in order, but I like to put it in order. So what I'm going to do is I'm just going to bring this down. I like to be systematic about it when I set it up. And so we got ACE, Then we got ADE, BCD, BCE, BDE, and then finally, there's only one other possibility, is CDE. Okay, everything else would be just a repeat of those. All right, so let's do the minimum. So in this example, ABC, guys, would be 10, 5, 10, okay? So I'm just going to put that here, 10, 5, 10. ABD would be 10, 5, 7, according to the data. ABE would be 10, 5, 9. ACD 10, 10, 7. ACE is 10, 10, 9. Okay, ADE is 10, 7, 9. BCD 5, 10, 7. 5, 10, 9. 5, 7, 9. And last one is 10, 7, 9. And now that we have the data, we can find the sample minimum. So the sample minimum is the smallest number. The smallest number here is 5. Here is 5. Here it's 5. Smallest number here is 7. Smallest number here is 9. Here it's 7. Here it's 5. Here it's 5. 5. And then the smallest number here is 7. There you go. And that's our that's it for that. And then we're going to go ahead and graph that. So there appears to be 2, 4, 6 5s and 3 7s and 1 9. Okay. 2, 4, there's 6 5s, 3 7s, and 1 9. There you go. So that's our sampling distribution of sample minimums, or so minimums. All right, now let's look at the part B. So now we're going to do the proportion of females for each sample, and we're doing size n equals 2, okay? And there's 10 possibilities. All right, so the proportion of females, that's what we want, okay? Proportion of females for each sample. All right, so A is Abigail is female, Bobby is male, Carlos is male, Diana is female. So basically the only two males are B and C, okay? So we'll just keep that in mind. B and C are males, the other ones are females. So we're going to list, and we're going to, remember this has to be 2 of them. They can't be 3. Sample size is n equals 2. All right, so we got A, Abby, and Bobby. All right, and then we can have Abby and Carlos, Abby and Diana, Abby and Emily, then Barbie and Carlos, Bobby, Diana, Bobby and Emily, Carlos, Diana, Carlos, Emily, and Diana, Emily. So those are the 10. So remember, the only ones that are male are B and C. The rest are female. So here, the percentage of female is 1 out of 2, right? Which is 50%. So 0.50. Again, we got that by doing 1 out of 2, right? That's our p hat. Remember, sample proportion is p hat. All right, and then here A and C, again, that's another 50%, okay, 0.50. A and D, those are both females, so that's going to be 1, all right, so because it's 2 out of 2. A and E, again, those are both females. B and C, that's 0 out of 2, which is 0. This is going to be 0.50, 0.50, 0.50, 0.50, and 1. Okay, so then we can graph that. And we have 1, 0. We have like what, 6.50s. And we have 3 1s. All right, and that's a sampling distribution of the proportion. Now I want you to notice the shape of these graphs. The sample distribution of sample proportions appears to be roughly symmetric, roughly. And the sampling distribution of sample minimums is not. It appears to be skewed, right, to the right. So it has a skewed nature to it. So this is going to affect the sampling distribution. Okay, so these are things we want to consider. We'll get to that concept later. But that's how you do that. So learning target number 3, use the sampling distribution of a statistic to evaluate a claim about a parameter. Example 3. We're going to just dive into an example to show you how to do this. Okay. Now, to determine how much homework time students will get in class, Mrs. Lin has a student select a simple random sample of 20 chips from a large bag. The number of red chips in the simple random sample determines the number of minutes in class students get to work on homework. Mrs. Lin claims that there are 200 chips in the bag and that 100 of them are red. When Jenna selected a random sample of 20 chips from the bag without looking, she got 7. So the first thing we want to address is what is the evidence that less than half of the chips in the bag are red? Okay, so what is that evidence? What does it look like, right? So first off, Jenny she only got 7 red chips out of 20, and 7 out of 20 is less than half. So that's our first piece of evidence. Okay, it is from Jenna's sample. Her sample proportion was in this case 7 out of 20, right? So 7 out of 20, which is 0.35. Okay, so that was her p hat, and this is less than 0.50. So that's our first evidence that we have less than half of the bag of the chips are red. But is that convincing evidence? Could this have happened due to chance? This is what we want to answer. Now, provide 2 explanations for the evidence. Well, there's a couple of explanations, right? The first explanation, it's possible that Mrs. Lin is telling the truth, and Jenna just happened to get a p hat less than 0.50. Due to chance or due to sampling variability, right? Because sampling variability is something chance-based, right? So we have sampling variability. It is also possible that Mrs. Lin is lying and that there are actually less than half of the chips that are red in the bag. Okay, so those are our 2 possibilities. We want to see which one is which. So we use technology to simulate choosing 500 simple random samples of size n equals 20 from a population of 200 chips, assuming that we had 100 red, 100 blue. So that's the dot plot shown here. There is 1 dot in the graph at 0.80. So we want to identify this 1 dot right here. So what does that dot represent? We want to adjust that. Okay, so that dot represents where we have a simulation where we have a simple random sample of 20 chips that we select, and we do this, and we get 16 red chips. Okay, because 0.8 is 16 out of 0.8 is 16 out of 20, right? So 16 red chips out of 20. That's how we get the 0.8. Okay, so in a simulated simple random sample of 20 chips, there were 16 red chips. So p hat is equal to 16 out of 20 equals 0.80 for this sample. All right, so that's that one. So D. Now let's answer the question here. Would it be surprising to get a sample proportion of 0.35 or smaller by chance? Like, would it be surprising to get that result and justify? All right, so again, remember we wanted to see that if her result, Jenna's result, right? We want to see if Jenna's result would have happened purely by chance. And Jenna's result was 0.35, so that's why we did that here. Okay, so let's look at it. 0.35. So if we look at here, 0.35, that's going to be all of this right here, right? All of that. And that does look to be, remember our cutoff is 5%, right? So it looks like this looks to be greater than 5%. And remember, we want it to be less than 5%. If it's less than 5%, that means we would be surprised by that result, right? However, because it's greater than 5%, we're not really surprised. It would happen due to chance, okay? So we're going to say no, we wouldn't be surprised by the result because there were many simulated samples that had a p-hat value of less than 0.35. Okay, so now we want to, the last part of the question, based on the previous answers, is there convincing evidence that less than half of the chips in the bag are red? Remember, convincing evidence means that the probability has to be less than 5%, okay, or which is 0.05. So it has to be less than that. Now, it's because we said it's not surprising to get a p-hat because it's greater than 5%, then unfortunately, then there isn't convincing evidence here. So there isn't convincing evidence that less than half of the bags and the chips in the bag are red, which means that it's just possible that Jenna, by chance, picked 7 chips out of 20. All right, so learning target 4, distinguish among the distribution of a population, the distribution of a sample, and the sampling distribution. This should say sampling distribution. Sampling distribution of a statistic. Okay, so again, remember, one of the things is how does the sampling distribution differ from the other distributions we looked at? So this is what we want to look at. There's 3 different distributions. One of them is the sampling distribution that we were talking about in this lesson. Okay, so we're going to use example 3. Example 3, if you recall, had to do with the chips, right? The red and the red chips, right? So there's the number of red chips in the bag. Okay. All right. So we're going to be using that example for this. So using example 3, there are 3 different distributions that are involved, right? When we sample repeatedly. The first one is the population distribution. So the population distribution is basically what it sounds like. You're doing the entire population. So it gives the values for all individuals, right? So for all the individuals in the population. So in this example, the individuals are the 200 chips, right? And the variable we're recording is color, right? So we're recording the color. So our parameter of interest is we're trying to do the proportion of red chips, right? So proportion of red chips. And so we're going to use P for the parameter, which is the 0.50, okay? That's what they were saying, is that the P is equal to 0.50 for the population. All right? So if we were to graph the population distribution, it would just look like this, because we're supposing that the parameter is P equals 0.50, which means that 50% is blue, 50% is red, and there's 200 chips in total. Therefore, this is our population distribution, okay? So that's number 1. So let me just put number 1 here. This is number 1. All right, and then number 2 is the distribution of sample data. So what it does, it shows the values of the variable for the individuals in a sample instead of a population. Okay, so you're taking a sample from the population and displaying those results. So in this case, the distribution of sample data shows the values of the recorded of the variable color. I'm sorry, for the 20 chips, right? So we took 20 chips out of the bag. That's what Jenna did, remember? So for each sample, we record a value for the statistic, and that would be called p-hat. And p-hat is the sample proportion of red chips. Okay, so if Jenna went ahead and picked from the bag, from this population, and she picked 20 chips, she could have a p-hat of 8 out of 20, which is 40%. So she could have picked out 8 red out of 20. If she did it again and if she put the chips back in the bag, shuffled them up, and did it again, well, she could have 11 red chips, right? Because this is what we refer to as sampling variability, right? Where the samples vary. So here I'm going to say the samples vary because of sampling variability. And so the distributions of sample data, so that's what we're doing. So these are the distributions of sample data because they're coming from the sample itself. Okay, so these are different distributions of the sample data. There's 2 different ones here. Okay, so this is number 2. So again, this is a distribution of sample data, and then this is another one. Okay, so I just want to make that clear. All right, so now if we took them and we found the p-hat, right, the statistic, we would get 0.40 and 0.55. Then if we graph these and we put them in a graph and did this for all the different p-hats, we would get the approximate sampling distribution. This would be number 3. Okay, so number 3, the sampling distribution of the sample proportion. It displays the values of p-hat from all possible samples of the same size. All right, and notice the shape of this sampling distribution of p-hat. Okay. All right, so those are the 3 different ones. You want to make sure you understand each type of distribution. So remember that a sampling distribution describes how a statistic varies in many samples from the population. However, the population distribution and the distribution of sample data describe how individuals vary. Okay, so the sampling distribution, the main difference, is talking about how a statistic varies, whereas the other ones talk about how individuals vary. All right, so example 4. The following is a dot plot of the AP Statistics exam scores for all 253 students in a large district. What kind of distribution is shown on the right? Circle 1. So we got the AP exam scores for all 253 students in a large district. That's a population for all the students in there, right? So right here, if this is a lot of students got 1s and 2s, a lot got 3s, 4s, and then 5s, right? So this is for all the people. So this is a population distribution, all right? So that's that. Now, let's just suppose we take a sample from the 253 students. So sample 1 is we take a simple random sample of 10 students, and we graph them, and then we're going to graph them in a dot plot, okay? So let's suppose that we do this. So we're going to show you how to run through this process. You guys have a sheet at the very last part of this packet, right here, the AP exam data for example 4. And what we're going to do is we're going to randomly select 10 folks from here. So each student is numbered from 1 to 250. Notice. You can see that here. It's a little hard to see. Zoom in. So you have student number 1, student number 2. Student number 1, their AP exam score is 3. Student number 2, AP exam score is 1. So what we're going to do is, using a random number generator, we're going to select 10 random 1s here. Okay. All right, folks, so we got a graphing calculator, and what we're going to do is we're going to randomly select 10 students from our sample, remember from 1 to 250. So we're going to hit second, or actually not second, sorry, scratch that. Let me clear that out. We're going to hit math, and then go to use the right arrow to go through the tabs. You want to go to the probability tab, and we want to go down to random int, rand int, okay? That's for random integer. Okay, and that's going to be our random number generator. And so our lower value is going to be 1, and remember we're generating 10 random numbers from 1 to 250. Okay, 10 different numbers. Okay. Okay. So now at this point you can change this n and say 10 for 10 values, and it will give you 10 random values. However, I don't suggest doing that because for this example is because you could have the same value repeated again. And remember, we want to have different values. So I'm just going to leave it by default and just leave it from there, and it's going to just do 1 at a time. Okay, so my first is 200. So I'm going to write that down somewhere. So we have the 200th student so far. And then we're going to just hit enter again. We got 238. And we'll just kind of repeat that. So 56, 93, 2, 234. That's not a repeat, so that's good. 28, we haven't repeated that yet either. 8. That's so see that's a repeat. So we're gonna repeat that. 138. So far we got 1, 2, 3, 4, 5, 6, 7, 8. We need 2 more. 214 and 245. Okay, so again, we're ignoring repeats. And let me just double check the data here. So we got 93. Okay. And then 238. Okay. So now that we got that, we can select our data points. So the first one is the 200 student. So the 200 student has an AP score of 1. Okay. So I'm going to go ahead and list these results back in the other page. Okay. And if you want, you can use your own results, or you can just use the results that I have here. But it's good practice. All right. So we're going to list out those AP exam scores. So let's do that right here. So we said we got 200, or no, the 200 student had an AP exam score of 1, and then I'll go ahead and list out the rest. All right, so I went ahead and listed out the AP scores based on the students that I've chosen and that sheet with all the data. Okay, so this is what we have, and we're going to graph this in the sample1 dot plot. Okay, so okay, so I'm going to here do, this is going to be a score of 1, score of 2, score of 3, score of 4, and a score of 5. Okay, so that's how I'll do it. And I really shouldn't be doing it that sharp. So I'll just do it like that. Okay, so now we're going to do our dots. So we have 1, 2 1s. We have a 1, 2. We have 2 3s. We have 2 4s, it appears. And we got 1, 2, 3 5s. Okay, so there you go. So what kind of distribution is this that we just graphed? Well, this is the distribution of sample data. Okay, so this is the distribution of sample data, not a sampling distribution. So you want to know the difference. Okay, so so let's just suppose we take another sample. Sample 2, we take another random sample of 10 students, and then we'll do this for sample 3 as well. So I'm going to go ahead and use the random number generator and select another 10 for sample 2, sample 3, so on and so forth, and then we'll go from there. So I'll go ahead and do that. All right, so went ahead and took the other two samples, using the random number generator on the calculator, random int, and then just figuring out which student from that had the AP score and listing them out. So we have taken 3 samples, simple random samples of size 10 so far. All right, so what we're going to do is we're going to calculate the proportion that passed. Okay, so that means they got to go level 3 or higher, or yeah, so 3 or higher. So 3 or 4 or 5. Okay, so looking at sample 1, it appears that we had a 1, 2, a 5 and a 4, a 3, 1, 2, 3, 4, 5, 6, 7 pass. Okay, so we have 7 students that appeared to pass out of 10. Okay, for this, so sample 1, the p-hat is 7 out of 10, which is 0.70. Okay, which is just 0.7. Now sample 2, we have a 5, so that's 1, 2, 3, 4, 5, 6, 7. Again, it looks like we had 7 pass because we have, yeah, so it looks like it's another p-hat. So 7 out of 10 is 0.7. Okay, and then we'll do the next one. We have 1, 2, 3, 4, 5, 6 pass for this one. Yeah, so it looks like we have 6 pass for this one. So it's 6 out of 10, which is 0.6. Okay. So again, these are different due to sampling variability. These happen to be the same, right? but again, this is going to be different due to sampling variability. Now we're going to graph the proportions on the graph on the right, in which multiple samples were already taken. Okay, so all right, and we're going to actually do these in red. So let me just highlight this in red, and I'm going to include it in here. Okay, so we're going to graph this. So 0.7, and then 0.7, and then we had a 0.6. All right, there you go. All right, so, and the rest of the data is when we take other multiple samples and then graph them. But here we only did 3, but this is just data that we had done in the past where we did this multiple times. And then this is the graph that we get. So what kind of graph do we have here? What kind of distribution? Well, this is a distribution for p hat, right? So that means this is a sampling distribution of sample proportion. So this is the sampling distribution, and I'm going to put in parentheses of p hat. Okay. So now you know, hopefully you know the difference between the 3 distributions, right? And so that way you can understand that learning target. All right, so now what does, in this case, what does each dot represent? So each dot represents one simple random sample, right? So one random sample of 10 students and a sample proportion p hat calculated from that sample. Okay. All right, go ahead and pause the video and see if you can try the check. I'm going to go ahead and scroll down so you can see it. So this is the first part. All right, and then this is the second part B. And then this is part C. So go ahead and pause the video and see if you can try it. All right, so hopefully you tried it, and you can now check your answer. So Mars Inc. says that the mix of colors in its M&M's milk chocolate candies from its Hackstown, New Jersey factory is 25% blue, 25% orange, 12.5% green, 12.5% yellow, 12.5% red, and 12.5% brown. Assume that the company's claim is true and that you will randomly select 50 candies to estimate the proportion that are orange. Okay. So we want to estimate the proportion that are orange, and we have to select 50 candies, and then they give you the amounts, right, for each color, assuming that that's for the population, right? All right, so first thing we want to do is identify the population, parameter, sample, and the statistics. So this is basically the first learning target, so just to practice it. So in this case, the population is all the M&Ms, right? So all the M&M chocolate candies produced by this factory in Hackettstown, New Jersey, right? So all of them. Okay, so we're going to go ahead and write that. So the population, it's all M&Ms, milk chocolate candies, produced by Hackettstown, New Jersey factory. Okay, and then the parameter we're dealing with proportion, percent, right? Percent, decimal, fraction, that kind of thing. That's going to be P. Okay, so the proportion, the symbol is going to be P, which is the proportion of all M&Ms. Candies produced by the factory, okay? By the New Jersey factory. I'm just going to shorten it. All right, now the sample. The sample, we're dealing with our population, our sample of interest is for the orange candies. So we're interested in the orange candies, okay? So, by the way, we forgot the parameter that was claimed here. The claimed parameter for orange, right, is P equals 0.25 for orange candies. according to this value here. All right, so now this the sample, we took 50 candies, right? So 50 M&M's candies, randomly selected. Okay, and then we have the statistic is what did we get for that that. So the statistic is the proportion of the sample of 50 M&Ms that are orange. And the symbol for that is p hat. Okay, now we don't know what that is because they didn't give us that they didn't give us what that specific p hat was for that particular time. But so there you go. That's a description. Okay, so the next thing is they want you to graph the population distribution. All right, so we want to graph that. We got blue. We're going to graph blue, which was 25% blue. Okay, so we got 25% blue. Then we got, now this is this is not a histogram, guys, so the bars don't have to touch. This is just a bar graph, okay? The orange was also 25%. The green was 12.5%. The rest of them were 12.5%, so I'm just going to do that. All right, so there you go. So that's our population distribution, right? So part C is imagine taking a random sample of 50 M&M's milk chocolate candies. The graph below shows a possible distribution from that sample. What kind of distribution is it? And give the value of the statistic for this sample. So this graph shows a possible distribution of sample data, right? That's what they're saying there. Okay. So what kind of distribution is it? It is a distribution of sample data. Okay, so that's what this is. This is from a specific sample. That's why the here actually the values, this should be the wrong graph, so I'm going to go ahead and replace this. So this graph should be different. All right, guys, so I went ahead and changed the graph. Sorry about that. That graph that I had earlier was the same graph as what we had here, which was the population distribution. I didn't mean to put that there. I meant to change it up. So suppose we have this as our data. Here, notice that we have frequency, so I would suggest just kind of just doing the graph here, down here or something like that, or just change the numbers here. But here we have 18 brown, we have 18 blue, 8 brown, so on and so forth. Okay, so this is a distribution of sample data, and we want to give the value of the statistic. Okay, so what's the value of the statistic? The statistic is we're dealing with orange, right? So we want the proportion of orange. So for orange, it appears there are 9 that were selected, right? So let me just kind of go there. Yeah, so there appears that it's 9 here. So it's 9 orange, so that means that it's going to be p hat is 9 out of 50. Which is 18% or 0.18, okay? Or 18%, same thing. All right, so that's the value of the statistic for that sample. Okay, so now it says which of these graphs, and notice that I have this here, so which of these 3 graphs could be the approximate sampling distribution of the statistic? Explain your choice. So it can't be this one because we said that this one is the distribution of sample data, right? So then which of the other graphs in that case could be the approximate sampling distribution? Okay. So in this case, let's look at the other two, the middle one and the one on the right. So according to the company's claim, the orange should be about, orange should be about 25%. So it should be 25% orange, right? So if I look at the center of this graph here, this looks approximately symmetric, by the way, guys, right? Approximately. And so the center of that is roughly at 25%. Okay. And if I look at this graph, it does look approximately symmetric as well, but the center of it seems to be around here, which is around 12.5%, right? 0.125. It looks to be between 0.10 and 0.15, whereas this one it seems to be about 0.25. And remember, according to the company's claim, it should have been 0.25. So it looks like the graph in the middle should be the approximate sampling distribution of the statistic, okay? Where it should be on average 0.25, not 0.125. Okay, so here we got the middle graph is the approximate sampling distribution of p hat. The statistic measures the proportion of orange candies, so say candies, sorry about that, in samples of 50 M&Ms. All right, so assuming the company is correct, that means 25% of the M&Ms are orange, so the center of the distribution of p hat should be at approximately 0.5, right, or 0.25. Now, the first graph, or the one on the left, right, the first graph shows the distribution of the colors for one sample. All right, so that's the distribution of sample data. And then the third graph, the one on the right, is centered at 0.125 rather than 0.25. All right, and that is learning target number 4, guys. All right, so learning target number 5 is states that determine if a statistic is an unbiased estimator of a population parameter. So now we know what a sampling distribution looks like. And so now what we want to do is we want to determine if the statistic that we calculate, whether it's p hat, whatever, is unbiased. Okay, we know that the p hat is supposed to estimate p and all that, and we know that the mean has to estimate the X bar has to estimate mu, things like that. But is it unbiased? Okay, so what is an unbiased estimator? An unbiased estimator is a statistic that is used to estimate a parameter that such that the mean of its sampling distribution is equal to the value of the parameter being estimated. Okay, so for example, if I'm doing a sampling distribution of p hat, then the mean of that graph, right, has to equal to the value p itself. So in this example, we're dealing with p hats here, and the average of this sampling distribution was 0.25 because it's at the center, right? So we said that basically the mu of p hat is 0.25, but that was equal to the p, right? The p was the true proportion value for the orange candies according to the M&M's company, right? And it actually matched up with the average of that sampling distribution. This is exactly what we're talking about. So in this case, this is an unbiased estimator, p hat, right? So that's what we mean by unbiased estimator, is that the mean of the sampling distribution is equal to the true value of the parameter that you're trying to estimate. So again, so unbiased, what's unbiased mean? Remember, unbiased means that you're basically consistently or you're not consistently too high, too large, or too small, right? Too small or too large when you're taking many random samples. Okay, so you're not too far away from the true value, or you're not too close to the true value, right? You're not too small, you're not too large. Biased means that you're consistently overestimating or underestimating. Okay, so you're consistently under or overestimating the parameter. Okay, so you're consistently less than or greater than the parameter. Okay, so example 5. Let's revisit the sampling heights example. Remember the four suns where they had the height of 71, 75, 72, 68 inches back in, I think, example 2. So we want to revisit that example. So here again is the sampling distribution. This is what we had graphed earlier for sample size 2. Okay. Now, is the sample mean an unbiased estimator of the population mean? Okay, so this is the distribution of sampling means right now, right? The sampling distribution of sample means. So we're going to take the sampling distribution and find the average of it. And if the average of it matches up with the parameter value, which the parameter here is mu, right? The population average of their heights. Then if it matches up, then it's unbiased. If it doesn't match up, it's not unbiased. Okay? All right, so let's do that. So what we're going to do is to determine if the sample mean is an unbiased estimator of the population mean, we need to compare the mean of the sampling distribution. Okay, and the mean of the sampling distribution, the symbol for that is mu x bar. So that's the symbol right here. Okay, so we need to calculate that, and we want to compare it to the value we're trying to estimate, which is the mean of the population mu. All right, so we're trying to compare the mu x bar with the mu. So the mean of the sampling distribution, let's go ahead and calculate it. The mean of the sampling distribution. Remember that this is the sampling distribution, and these are the values, right? We had this is a value of 69.5. This is 70. We have 71.5 plus 71.5. We have a 73 and 73.5. So we're going to add those values up and then divide by 10, because that's how many we had, right? I think there's 10 there. 6. I'm sorry, 6. Divide by 6. Okay, so let's go ahead and do that real quick. Okay, so we got 69.5 plus 70 plus 71.5 plus 71.5 plus 73 plus 73.5. All divided by 6, and we get 71.5. Okay, from that. So that's the mu x bar. Now we're going to calculate the mean of the population. So what's the population? Well, the population are these guys. There's only 4 suns. That's the population. And we want to average those heights. So we're going to do 71 plus 75 plus 72 plus 68 divided by 4. Okay. All right, so 71 plus 75 plus 72 plus 68 divided by 4. And if we calculate that, guess what? That gives us 71.5. Well, you look at that. So when we did the sampling distribution and we averaged it, the values in the sampling distribution, we get the exact same average as the average for the population. So because these values are equal, that's going to suggest that x bar, the sample mean, is an unbiased estimator of the population mean mu. So in this case, mu x bar was equal to mu, right? Okay, so in the sampling heights example, again, going back to the example, we did a size n equals 2, right? We did the 4 suns, all that stuff. And we did the sample range. I believe in part B, we did sample range. So let's go ahead and do, this is the graph that we had for the sample range. So what we're going to do is the sample range unbiased, an unbiased estimator? Okay, so what we need to do is calculate the mu of the sample range of this distribution, the distribution of sample range. Okay, so we have a 1, we have 2 3s, we have 2 4s, we have a 7. That's a total of 6 values. So let's go ahead and add those up. So we'll do that real quick. So we got 1 plus 3 plus 3 plus 4 plus 4 plus 7 divided by 6. Those are the sampling ranges that we had, and we got 3.67. Okay, so that's our mu sample range. Now, the range of the population, we want to compare it to the range of the original population. Remember, this is the population. So what's the range of 71, 75, 72, and 68? Well, the range is the largest minus the smallest. So it's going to be 75 minus 68, right? So 75 minus 68. Oh, it already shows it here. Sorry, I wasn't doing it wrong. 75 minus 68 is equal to 7. All right, so 3.67 is not equal to 7, guys, right? Because the mean of the sampling distribution, 3.67, is not equal to the value it is trying to estimate, which is 7. The sample range is not an unbiased estimator. Okay, so in this case, the mu of sample range does not equal to the population range. Okay, so therefore it's therefore it's not an unbiased estimator. Okay, so go ahead and pause the video and see if you can try the following problem. Again, you're going to use these two graphs to help. Okay, so let's go ahead and take a look at it. So it says, suppose the population variance sigma squared is 9. Which statistic is an unbiased estimator? So we're going to circle the graph. So they tell you that the graph on the left uses this formula right here, which is the formula for the variance, right? It's using that formula. And the graph on the right uses this formula for the variance, okay? So the only difference is that this one uses n minus 1, this one uses n. Okay, so which one's going to be unbiased? Well, we're going to do is we're going to look at the value on the left. So let's look on the value on the left. So the mean is around here, right? And that's a value of about 9, right? So this is the distribution of sample variances, okay? So the mean of the sample variances, S squared. Remember, variance here in this case is S, well, yeah, this is going to be for S squared, or yeah, S squared. I'm just going to use that as a symbol because the symbol for variance is usually S squared. All right, for the sample variance. All right, so we got the mu of S squared is equal to 9. Let me just put S squared for this one here, and then S squared for this one here. All right. And then the mu of S squared, and I'm going to put here n minus 1, and then this one S squared n of n, okay? Here, the mu S squared is actually going to be not 9, but it's going to be smaller than 9, right? 1, 2, 3, 4, 10, so it's actually going to be 7 right here, so about 7. Okay, so then which one is closer to the population variance? Well, the population variance is sigma squared equals 9, right? So it appears that this right here is equal to, for graph number, I'm going to call this graph number 1, and then graph number 2. For graph number 1 is equal to the population variance of 9. Whereas this one right here, mu S squared for graph number 2, is not equal to sigma squared. And therefore, the one on the left is an unbiased estimator. The one on the right is not an unbiased estimator. So we're going to graph we're going to graph this one right here. This one is the unbiased estimator. So this is important, guys, because this is why in your formula we use n minus 1 down here. Notice that? So you may have wondered in the formula sheet, why did they use n minus 1 for the standard deviation, right? For the sample standard deviation and not n? Well, this is why. Because if I introduce the n minus 1, it makes it an unbiased estimator. If I just do divided by n, it makes it a biased estimator. Okay? All right, that's an important concept to understand. And that's it for that learning target. So, learning target 6, describe the relationship between sample size and variability of a statistic. So what makes a good estimator, an ideal estimator? Okay, so ideally, if you have an estimator, a statistic that is used to estimate the population parameter, um, that sample statistic ideally has to have no or low bias. Okay, so in other words, it has to be an unbiased estimator. This is why we need to understand what unbiased estimator means. And so we need that estimator to have that unbiased. And this is why we used the formula for S squared has an n minus 1 on the bottom instead of an n, because we want to make sure that it is as unbiased as possible. Okay. It also has to have minimal variability. Okay, minimal variability. Variability means change, right? So it can't be changing too much. It has to have minimal change, right? When you're taking from one sample to the next. So again, you decrease variability by increasing the sample size in general. Okay, not just the number of samples, right? We're not talking about the number of samples. We're talking about the size of the samples. So, for example, an n equals 2 sample to n equals 3 sample or 4 or whatever. So remember the Abby, the Carlos example, right? You might choose, instead of just choosing 2 people at a time, you might choose 4, right? Their sample size is 4. Or instead of choosing 2 candies, you might choose 4 candies for each sample, okay? And you might do that 50 times, whatever. But this is what we mean by increasing the sample size, okay? So the spread of a sampling distribution does not depend on the size of the population, as long as you meet the 10% condition. All right, so remember that the 10% condition, what that means is that you want your sample size to be less than 10% of your population. That's what the 10% condition is, okay? So just to remind you. And what you don't want to draw too large of a sample, because if you draw too large of a sample without replacing the people, without replacement, then it's going to be too significant compared to the population, in which case then it's going to affect your results. Okay, so we want to provide as minimal disturbance to the population as possible while also being representative of the population. So it's a fine line. Okay, all right, so accuracy has to do with low bias. Okay, so accuracy has to do with low bias or unbiased, and precision has to do with low variability. Okay, so the difference between accuracy and precision is that precision means that you're more consistent, and an accuracy is how far you're off the bullseye, the target. Okay, um, so um, bias is your aim. So how far off is your aim from the bullseye? And then variability is how, if you're repeating your shots, how spread out are the shots? How consistent are they? Okay. So there's 4 options. You can have high bias and low variability. So notice that here there's a high bias here. But the variability itself is so high bias, but but here we have low variability, low spread, right? This is a V right here. Here you have a high variability, but you have a low bias, because on average, the targets on average are centered around the middle. So they're very, very low bias. Okay. Um, so yeah, low bias. So I'm just going to put here low bias. Now, for here we have high bias in average, right? On average. But here we have and we also have a high variability. Okay. And then the last one is we have very low bias and low variability. Okay. This is the ideal, right? This is the ideal estimator. This is what we want. Okay.
All right, so example 6. The figure shows approximate sampling distributions of 4 different statistics intended to estimate the same parameter. Okay, for 4 different statistics. Okay, so we have the graphs here, and what we want to do is and identify which statistics are unbiased estimators. Okay, so let's look at it. So so the population parameter for this one, they mentioned that the population parameter is there, right? That's where the population is, right there. Now, if you look at this graph, right, it looks to be skewed to the right, and so in this case, the uh, the mean of this distribution is going to be right around here-ish, right? So it's not going to be quite in the at the hump. It's going to be to the right of it because of the longer tail. So it's approximately around there, okay? So notice that it's off target. We have bias there. You see the difference between that and this value? So that's your bias, okay? That's not going to be an unbiased estimator. All right, and then here we have what appears to be an approximately uniform distribution. It's not perfect, right? But it looks approximately symmetric, okay? And since it's approximately symmetric, that means that the mean is going to be roughly in the middle, okay? So the mean, and notice that the mean, I'm going to do this in blue. So this and blue, and this here lines up with the blue. And this is the population, and notice that this is symmetric, approximately symmetric, and so the mean has to be in the middle, but notice that the red and the blue match up. Here, the population parameter is right here. This is approximately symmetric. However, in the middle, look at the distance between these two. So that's high bias, right? But notice that this has low variability, and this has high variability. You see that? And this has low variability, and this has a relatively high variability. Yeah, that has a high variability. Okay, so you can kind of get an idea of what we're looking for. So example 6, which or part A, which statistics are biased unestimators? So that's going to be graph number 2 and graph number 3. Those are unbiased because they hit the target. Okay, so number 2 and number 3 are unbiased estimators because the means of their sampling distributions appear to be equal to the corresponding population parameters. Now, which ones have high sampling variability? So we mentioned that it's going to be this one right here is high, the first one, and then the third one looks like so number 1 and 3. Okay. And then how can we reduce sampling variability? Okay, so we said statistics 1 and 3 have high variability because the data is widely scattered. Okay, we can reduce the sampling variability by increasing the sample size. Okay, so for example, from 20 to 100. All right, so which statistic does the best job of estimating the parameter? Explain your answer. So the best statistic here has to be the one that is unbiased and has a low variability, which appears to be statistic number 2. That seems to be doing the best job because low variability and unbiased. All right, so statistic 2 appears to be doing the best job at estimating the parameter. It is unbiased and has very little variability. All right, guys, that's going to do it for the video. Hope you found this useful and informative. And as usual, I'll see you in the next one.